All right, so good morning, everyone. So this is my pleasure to be here. I really would like to thank the organizers for giving me this chance to present some work about many-body physics with arrays of individual atoms, which we've been doing at the Institut Optics, which is also on the campus of the Université Paris-Saclay, the same as the institution that Pascal Senlar, the previous speaker, come from. And more specifically, in the next 20 minutes, I will devote my time trying to show you how we can implement.
One second. I don't think we can see your slides. There's a problem. Now we can see this. Thanks. Works now. Okay. You just go to presenter mode. Yeah. No, we don't see now. Yeah.
Oh, okay, so that's the problem because we did the test on Friday and it was working.
Mm-hmm.
All right. So let me just try to.
We can see it now. This works.
Okay, so
you just.
I will leave it like this then. So
Pascal also said she just wrote she didn't use full screen. There seems to.
Yeah, because okay, that was working on Friday when we did the test. But okay, so
okay.
All right. So I will use this mode then. So once again, thanks a lot for the invitation. And so I'm going to talk about some work we've been doing using arrays of individual atoms. And more specifically for this talk, I will concentrate on the implementation of a spin-orbit coupling using interacting Redbird atoms. So as I was saying, this is work done at the Institut Optique, which belongs to the Université Paris-Saclay, the same institution as the previous speaker. All right, so before I do so, let just me introduce you to the team who did the work. So more specifically for this work, it was the work of Pascal and Vincent, two PhD students working on the experiment, together with Daniel, who is a postdoc, and Thierry, who is a permanent staff member in our group, who guided the work. Very importantly for this work, we received a lot of theory input from our collaborator Hans-Peter Büchler in Stuttgart, together with his student Nicolas Lang and Sebastian Weber. And we also had a very interesting collaboration with Michael Fleischauer in Kaiserslautern. I also seized this opportunity just to advertise the fact that we're looking for PhD students and postdocs. So if you are interested, please contact me. All right, so what we're interested in is to explore topological states of matter. So as you probably all know, there are many examples of such states of matter, like, for example, quantum Hall effect, but also more recently topological insulators. And despite the fact that a lot is known about those states of matter, there is also a lot of unknown states. So, for example, of unknown questions. For example, the kind of open question that you may be interested in is to look at what happens if instead of having electrons, as is the case in condensed matter, you have bosons instead. What is the consequence of having underlying symmetries in the problem that may protect certain phases? What is the role of the interactions between the constituents? And of course, it leads to the fractional quantum Hall effect. And so the idea is to use the control we've gained over synthetic quantum matter, so to engineer a system that is specific to the study of those questions. And you all know that there are many of such systems. I mean, atoms, photons, ions, superconducting circuits are examples of such platforms onto which you can explore these questions. So more specifically, we would like to tackle the problem of topological states of matter in 2 dimensions. And so usually if you want to do that, you should have somehow some bond structures for the particles that exhibit topological properties. And one way to do it is to engineer an array in which the coupling, the hopping between one side to another in this array, or this lattice structure, is a complex number. So it means that it's described by a complex hopping here, j e to the I phi. Phi as a name, it's called the Pio's phase in this context usually. And so many platforms are implementing that. So for example, cold atoms in optical lattices, and we will probably hear from that in the talks of Monica just after this one, by shaking the lattice, by implementing artificial gauge field, by increasing the number of dimensions, going to synthetic dimensions. And other platforms such as superconducting circuits, for example, could also implement that, and then they tune this phase through, which is an Aharonov-Bohm phase in this case, by varying the flux through this plaquette. Photons have also been used to engineer some kind of chiral coupling. Usually, at the heart of all this, you need some kind of spin-orbit coupling and some time reversal symmetry breaking. And in views of exploring also the very challenging regime where the interactions between the particles are important, you would like that the bands are flat so that the kinetic energy is smaller than the interactions. So this is in views of reaching the fractional quantum Hall effect. So here, I will not show you that. I will just show you how we can use Rydberg atoms in order to implement the spin-orbit coupling, which is necessary to create the spin-orbit coupling. The platform we are using is these arrays of individual atoms. So this is a single-shot image of an ensemble of atoms. Each of these dot here, this bright dot, corresponds to the fluorescence of one and only one atom, which is trapped in a tightly focused micrometer size dipole trap. We can now operate up to 200 atoms. We can arrange them in very different arbitrary geometries. So for example, you can have this kind of honeycomb lattice. You can create this kind of snake containing up to 200 atoms, so with no defect. They are kind of assembled. We can also assemble any kind of arbitrary pattern. So this is just an arbitrary pattern, which is a pixelized versions of the Mona Lisa. It's useless for physics, but it shows the control over the pattern you can create. And we can even go to 3 dimensions in order to create this kind of Fulleren-like pattern or this kind of Eiffel Tower type of things, which once again is not too useful for physics. The atoms in this array are separated by several micrometers, which means that naturally, if they are in their ground state, they do not interact. So in order to make them interact, we promote them to Rydberg state, which are highly excited state of atoms, into which they, when they are in those states, they have 2 important properties. First, their lifetime is extremely long with respect to low-lying transitions. So for us, it will be the infinite, despite the fact it's only 100 microseconds. And second, they exhibit very large dipole moment transitions, which scales like the square of the principal quantum number of the state, and which is reminiscent of this solar model of the electrons, of the atoms, where the electrons spirals very far from the nucleus. And the consequence of this large dipole is the fact that 2 atoms, even at few micrometers distance, will exhibit strong dipole-dipole interactions. The order of magnitude of the interactions is the following. If you just take typical principal quantum number we use in the lab, distance about 10 micrometers, then the strength of the interaction is in the megahertz range, which indicates that the timescales for any dynamics driven by the interaction is sub-microsecond. And now you understand why this 100 microseconds is long enough, because it's much longer than the timescale associated to the interactions. So what I'm going to discuss in the next 5 minutes in the next 15 minutes, are the resonant, how we can use some resonant dipole-dipole interactions between Rydberg atoms and how it maps onto spin systems. And then I will enrich the atomic structure in order to implement the spin-orbit coupling. All right, so let's start with the resonant dipole-dipole interactions between Rydberg atoms. This is a level structure of the atoms we use. So we use rubidium-87. So they are initially prepared in a very well-defined state, and we excite them by lasers to the state 60s1/2. And I'm going to totally ignore for the time being and all the low-lying state. And for the remaining of the talk, everything I'm going to discuss is going to happen in the Redbird manifold. So here I just consider a nearest neighbor state, Rydberg state, 60sp1/2, which is connected by a dipole transition, electric dipole transition, to the 60s1/2 into which I have prepared the atoms. So now if I just take 2 atoms close by, the consequence of the interactions between the atoms is the following. If you prepare one of the atoms in the p state, the other one in the s state, then the interaction between them is going to induce a drive of spin flip, if you wish to speak in terms of spin language, of the state of one atom which goes down while the other one at the same time goes up. So these implement what is called an exchange Hamiltonian, sigma plus, sigma minus, plus sigma minus, sigma plus, in terms of spin language, and those are the Pauli matrices. So we can measure that directly on the experiment. So if you assume, for example, that you prepare 2 atoms separated by 30 micrometers, which is already a very large distance on the atomic length scale, and you prepare one atom into state P, the other one into state S, and you let the system evolve as a function of time, and then you measure what's the state of each atom. What you observe is that indeed the 2 atoms exchange their state. I mean, those 2 oscillations are actually out of resonance. They correspond to the probability for the first atom to be in P or the second atom to be in P, and we do observe an oscillation in phase opposition at a frequency which is actually the strength of the dipole interactions, which we can check as a function of distance. Very importantly, you can change the language here and just decide that now those two interacting atoms, which corresponds to the exchange of one p excitation between them, leads to single particle physics of the p excitation seen as a particle, which would hop from a site A to a site B, the site being materialized by the frozen atoms. So once again, two interacting Rydberg atoms, you go to single particle physics of a particle hopping from site to site. We have used this fact recently in order to implement a topological model, which is called the Sushrifer or the Eger model for bosons. And we've even been able to access the interacting regime to prepare what is called a symmetry-protected topological phase. And I will not give you any details about that. I will encourage you to listen to the talk of Sylvain Delesluc, who was the PhD student who did this experiment in our group like a year ago, and we'll give you more details about that. What I want to do instead is to make the interaction slightly more complicated by enriching the atomic structure. So what I'm going to do now is to discuss the resonant dipole interaction in a three-level structure and show you that you can implement a spin-orbit coupling. And that was the result of a recent work here we published together with Hans-Peter Büchler. So let's go back again to those two Rydberg states, so 60s1/2, 60p3/2. I will use a combination of electric and magnetic field in order to shift the degeneracies between all the states and isolate just three states in this V configuration. So the three states I'm going to consider here are state 0, state minus, and state plus, which corresponds to different Zeeman state of these manifolds. So now I can put a second atom nearby at a given distance r with exactly the same kind of internal structure. And of course, those two atoms are going to interact via the dipole-dipole interaction, which is a d1.d2 minus 3 d1.r, d2.r. So that's the full tensorial structure of the dipole-dipole interaction. And now if you write this in terms of spherical coordinates, so the expression is a bit complicated, but so there are actually several terms, and I will try to walk you through the important ones for this, for what matters here. So let's first consider the situation where the first atom is placed in state minus, this state here, which is the excited state, the other one in state 0. Then, of course, you can first have the exchange of the state in exactly the same way as I was discussing in case of two-level atoms. So this is driven by this part of the Hamiltonian. That corresponds to essentially the exchange with an amplitude, which is the d minus square over r cube, where d minus is the dipole matrix element coupling those two states. So that's the first possibilities. And of course, if you just assume that you've got some kind of atomic plane, and those are just two atoms, so I mean, you can define the planes arbitrarily with any arbitrary axis in this plane and perpendicular to the magnetic field. Of course, this T minus is then isotropic. Okay, so that's the first important thing. But now let's go back to this, let's move to the second term, which is this term here. You see the appearance of a phase, and it turns out that this phase is the phase in cylindrical coordinate of this internanuclear axis with respect to the reference axis you've chosen, which at this stage is purely arbitrary. So now it turns out that this will induce a thin state exchange as well in the very same way as previously, but instead minus goes to 0, while 0 goes to plus. So you do not conserve the internal state of the atom in this way. And of course, this is an off-resonant process because there is an energy mismatch, mu, with respect to those two states. The thing which is very important to realize is that here there is now a phase factor which depends on the geometry. And this actually implements a spin-orbit coupling in the following way. If the excitation, the minus excitation, moves from one atom, atom 1 to atom 2, at the same time, the internal state of the excitation moves from minus to plus. So you've changed the internal spin of the atoms while the particle hops from one place to another one, hence the name spin-orbit coupling. So now let's look at the consequence of this spin-orbit coupling when I consider a triangle. And now I will show you that the phase phi, which I have introduced, which so far is arbitrary, is going now to have a very, very defined meaning imposed on the geometry by the geometry of the particles. So I just put the atoms on a triangle. So I will place a minus excitation on atom 1. Second atom 2 and atom 3 will be placed in state 0. Let's look at the Redbird manifold that I can have here. So essentially, this is the 3-atom state, energy state, when the atoms are either in state minus or in state plus. Based on the fact that there is an energy mismatch mu, of course, they are not at the same energy. So this one is more energetic than this one. So now what can happen? I mean, I can have the transfer of atom 1, which was initially in state minus, to 3. So essentially the excitation, the minus excitation hops from 1 to 3. And this can be done directly just by the T minus term, which I have introduced before. So just the exchange of the state of atom 1 and atom 3. But the second thing that can also happen is that I move from 1 to 3 through the site 2. And in this case, I can have a flip-flop where the state of the internal atom is exchanged from minus to plus. This, of course, comes at an energy cost, which is mu, and therefore it's an off-resonant process. On each of these processes, I pick up a phase factor, which depends on the phase phi 1, 2 and phi 2, 3 with respect to any arbitrary axis. But now, if I calculate what is the amplitude of this move, it's the product of the matrix element divided by the energy mismatch in perturbation theory, assuming that mu is larger than W and T minus. And now what is very important is that you see here the phase difference, which is no longer an arbitrary phase, it's just the phase imposed by the geometry of the triangle. So now, if I go in the complex plane, what do I have? I mean, if I want to have the full amplitude, I need to sum the two amplitudes, the direct one and the off-resonant one. So in the complex plane, I have T minus, and then the second order process W squared. And therefore, the full amplitude is this arrow here in the complex plane, which is now exactly a complex hopping with a period space phi, which is given by this angle here, which is reminiscent to the angle which is imposed by the geometry of the array. Let's try to look at the implication of this on a triangle. So now I go to the lab. We try to implement this triangle. So numbers are atoms separated by 11 micrometer, about 10 Gauss magnetic field, a few fraction of a volt per centimeter for the electric field. And with these parameters, the mu is on the order, so the energy mismatch of about 20 megahertz, and the T minus and W are on the order of a megahertz. So we are indeed working in this off-resonance situation and in perturbation theory. The consequence of this complex hopping is a chiral phase. And if we choose the phase of the spiral phase such that the total flux in this elementary plaquette is pi over 2, then we observe that indeed the minus excitation will hop from site 1 to site 3 to site 2. And this is seen here, where you have the probability of the minus excitation to be either on site 1, on site 3, or on site 2. And you do see that sequentially it hops from one side to another one. I mean, if you want to have a small movie, so we plot the center of mass in the plane here. So we observe this kind of characteristic chiral motion, which of course is damped at long time due to experimental imperfections. You can do an ab initio calculation of this, and that was done by Hans-Peter Büchler and his team. And we do observe that there is a good agreement between the theory and what we measure on the experiment. So now what I'm going to do, I'm going to switch the sign of the electric field, so reverse the magnetic field, sorry. And in this way, what we observe is that the chiral motion is reversed. So we have broken the time reversal symmetry. So indeed, what we have, that we see that now, instead of going from 1 to 3 to 2, reversing the magnetic field leads to an excitation hopping from 1 to 2 to 3, as is seen here, 1, 2, and 3. So that's the consequence of the spin-orbit coupling, and shows that we can implement that with the Redbird structure. So I should also point out that actually other systems have seen that, and in particular superconducting circuit, there are some recent work showing this. So I will be kind of brief on this, but just telling you that if you have this ingredient of this spin-orbit coupling, and we generalize that to a much larger structure than just this triangle, Hans-Peter Büchler and his team have done the calculation. So you just take a honeycomb array, as we can realize on the experiment, and they've demonstrated that in this elementary system, you can generate band structure with non-trivial geometry. So the topology, sorry, is set up by what is called the Chern number, which is the curvature of the bands across the Brillouin zone. And indeed, what they find is that depending on the exact value of mu, you can have different Chern number. And so typically, for the one we have here, you can have Chern number of -1 + 1, or Chern number of 2 and -2. When it's 0, it's trivial. When it's not 0, it's a non-trivial topology. And with that, they've even calculated what you should expect if you place one excitation, minus excitation on the edge, and what you should observe is the equivalent of an edge state here, where the excitation hops right on the edge without entering the bulk, unless at long time when the excitation ends. So this is what we expect on the experiment, and that's what we would like to implement, and which we have not done yet. Okay, so this is for future work. But now I would like to come back to this elementary triangle and show you that there is actually something highly non-trivial happening here, when now, instead of having only one excitation on the triangle, one minus excitation, we place two of them. So let's now consider the situation where instead of having -0 and 0 as I had before, I do a particle hole symmetry, and I have 0 here, minus and minus. This kind of particle hole symmetry argument should lead you to the intuition that the 0 should propagate in opposite sense with respect to the minus excitation. That's what we expect from the intuition. So if you have the minus, which is an excitation which rotates in one way, the particle hole symmetry tells me that the 0 should rotate in the other direction. Let's go to the lab and see what happens. So this is the very same experiment as before. We prepare now the atom 1 in state 0, and we measure what is the probability that 0 is on atom 1, 3, or 2. And here, for the very same parameter as before, instead of seeing a sequential hopping from one side to another one, we just see a symmetric propagation of the zeroth excitation between 1, 2, and 3, and coming back. So it means that instead we have a symmetric propagation, and therefore this particle hole symmetry picture doesn't hold. So what is the problem here? The problem is that we should go back to the underlying mechanism that leads to the complex hopping. So essentially, the fact that there is an off-resonant process going from 1 to 2 with a spin flip. But here, this spin flip is impossible because the second atom is already excited in state minus, and therefore the 0 cannot transform into a plus excitation, because this second atom already carries an excitation. So this is a consequence of a hardcore constraint, if you wish. And therefore, the off-resonant coupling is switched off based on the fact that there is already one excitation in state minus, and therefore it leads to a phase, Peierls phase here, which is now density dependent. So it depends on the fact that you already have an excitation on atom 2. So you would have an e to the i5 as before, but 1 minus n2. So this is a phase that is density dependent, and so this is reminiscent of what is called a dynamical gauge field, which could allow implementing some specific QED type or gauge field models. So I will not say much here, but actually you can re-express everything I've told you in terms of a 0 excitation, of the 0 being now the excitation, and it turns out that you can interpret the 0 excitation as carrying an anionic statistics in this context, this anionic statistic being actually given by phi. So this is an example of an anionic statistic implemented on this Redbird platform. So with that, I come to the conclusion, and I would like to hopefully I have convinced you that actually these arrays of atoms are a nice playground to explore non-trivial aspects of many-body physics, which I have illustrated here on just an instance of 3 particles. Of course, what we want to do next is to go towards the 2D in larger arrays, to implement the proposal of Hans-Peter Büchler, but also to reach the interacting regime, which is really the one where we are supposed to be able to reach fractional topological matter. And I should also point out that there is another line of research associated to this exchange model, which I have not discussed so much, but that's something we're exploring in the context of quantum magnetism. So with this, I would like to thank you for your attention.
a lot, Antoine. Thanks for this very nice talk, very clear. I don't see any questions yet in the chat, so maybe I can start. So Antoine, I was wondering, since you can also do 3D structures, go into the third direction, not stay confined to 2D, is there something interesting you could do in this direction of topological systems by going to the third dimension as well, including the third dimension?
Yes, so I'm not completely aware of any specific, I mean, we could do that for sure. I'm not aware of any specific predictions that were done in 3D in the context of this parallel space. So, I mean, I cannot give you, a definitive answer to this. For us, the real challenge at the moment is trying to explore the interacting case in 2 dimensions, because this is really what is the challenge at the moment. I mean, of course, the protocol that I've just showed you here is one more example of a platform which can implement single particle physics, but we really would like to explore the many-body physics. And what is interesting is to see how this parallel space, which is density dependent, impact the many-body structures in this kind of platform. So that's really what we're looking at. So in 3D, I would be thrilled to do anything, but I'm not aware of any specific predictions that would make it at the moment worth investigating per se.
Mm-hmm. There's one question now in the chat. How were the hyperfine levels of S and P isolated to implement the V level to perform spin-orbit coupling?
Yeah, okay, so that's a very good question. So the way it was done, so we've isolated that with an electric and a magnetic field. And so in this way, you can really ignore those states that are completely spectators if you have initialized the minus state precisely and the 0 state precisely. If you've done that, all the other transitions will be non-resonant for this. So we do not need to worry about them. There is also the choice of how you match the quantization axis in this structure, which is perpendicular to the plane of the array. So I hope I've answered your question, Shane.
There's another one now. We can take one more. How do you see atomic arrays and optical tweezers as a candidate for fault-tolerant quantum computing compared to trapped ions and superconducting circuits? Oh, that's a big one.
Well, that's a big one.
Shoot.
I mean, the only thing I can say that is becoming really competitive. So the thing which is the advantage of this Redbird platform, maybe with a reason it's connected to any atomic platform, is the intrinsic scalability. So you can go to a large number of particles, and now, but it's the same in Emmanuel's lab. I mean, we can operate more than 100 particles. So we're really in a regime which for the moment is still challenging for the ions on the superconducting circuit. The downside of that for the moment is the fidelities are a bit lower. But the thing is that they've caught up pretty rapidly, and over the last few years, Redbird platform have improved the fidelity by a lot. So now we are getting close to 90 or even higher, depending on the platform, to 99% on the entanglement generation in those platforms. Still not the 99.5 or 6 that the ions have, and we all know that going to these extra digits is hard, but very clearly these platforms is becoming more and more mature. So I'm hopeful that we will reach at some point fault-tolerant quantum computing. But the thing which I would like to convey is that even with the limited, so to speak, performances of the platform, we can already do very interesting science with that in terms of quantum simulations or even exploring some optimization through quantum annealing, for example.